the next CUbit. I take pleasure to introduce Dr. Krister Shalm. And Krister has been, so he's at NIST, with John McGorton here, and he's been working at NIST since 2012. And before that, Krister received a Bachelor in Engineering Physics at the University of Toronto, and then went on to do a PhD in experimental physics at the University of Toronto. And we were kind of roughly pursuing our paths at the same time. And after his PhD, which was with Steinberg, he went to do a postdoc at the Institute of Science. And we do there again. So Krister is known for many things. Being a science communicator is one thing that is quite famous for. But in addition to that, he's been doing some fantastic science. He's been recognized with multiple awards, and I've got to just tell you about two. In 2015, he and the experimental team, the full experimental team, got the physics world with the physics world breakthrough experiment of the year for the loophole-free belt test. In 2017, I believe, we got what you can. Great privilege to introduce Krister, and I'm really excited to hear what he's going to tell us about today.
Hey, well, thank you, everybody. Can you hear me okay? It's been I guess a couple years now since I've had to do this live and not on Zoom. So it's a real pleasure getting to actually speak in front of people again. And also want to say happy Valentine's Day to everybody, and choosing to come here to listen to this talk about quantum entanglement and some of the things we've been doing over at NIST. So today I'll be telling you about a new service that we're hoping to launch here in the physics department. This work is being done in conjunction with Paul Beal and Kate Stange in the math department. And it's going to be quantum entropy as a service. Now, there's a number of components that go into that you need to have to kind of understand all of the physics and everything that goes into this. And so I'm going to try and give people kind of a crash course in a number of different topics, including quantum randomness generation, some quantum information theory, statistics, and so on. And I want to start by just acknowledging the many, many collaborators that have made this Bell test happen internationally. Some of these people are in this room, but in particular, I'd like to highlight some of the contributions of Gautam Kavuri, who's the grad student who's done a lot of the work, Jasper Palfrey, who is a programmer who's actually making the nuts and bolts of the service come online. Turning in a web service is not trivial. And we also have Mohammed, who has done a lot of the theory work for this as well, who's another graduate student. So there's a lot of contributors that have helped out with this, and there's a lot of different sets of expertise that we need. And the reason I'm choosing to speak about this aspect of our work today is because a number of years ago, when CUbit was first being formed, Paul and Kate and we applied for some seed funding with the promise of trying to produce a quantum randomness service. And this quantum randomness service would use our loophole-free Bell test along with some of Paul Beal's cryptographic random number generators to produce what's called a randomness beacon. And this was going to be a service that would come online, be run here. And we're now very, very close to actually fulfilling this. And I'm hoping sometime within the next 3 to 6 months, we'll have this up and running. And we'll be using entanglement to do a non-trivial task that has a true quantum advantage. And we're going to be offering that to the general public. So briefly speaking, what is a randomness beacon and why would you care about such a thing? Well, it's a relatively new idea that was first started at NIST, and now there's randomness beacons that are coming on around the world. And the idea is you have the service that emits 512 bits of randomness periodically every minute. And you can use this for lots of different applications, but typically things that require some kind of fairness, and you need an independent source of randomness. So any kind of lottery or resource division, who gets audited, or whose child goes to what school, or any of those type of tasks where you want to divide things fairly and you want an independent source of randomness. This is a good cryptographic primitive for that. And the way these beacons work, it's not just that it's outputting these random bits, but it's creating a chain, and it's technically a blockchain, although it doesn't have all of the negative things associated with like Bitcoin. All you're really doing is taking, and we call these pulses. So pulse number 1, you create 512 bits, and there's some extra meta information. All of that information gets hashed and incorporated into the next pulse. And then that gets hashed, incorporated into the next pulse. And so if you were to go back in the future and retroactively change the contents of pulse 1, you could detect it because it would not verify all of the other pulses. So it's a cryptographic primitive that has been, again, it's being studied, and there's a number of interesting use cases for this, and it's kind of generalization. So I'm not going to spend a lot of time talking about how this works and all the intricate details. That could be like a semester-long crypto course. But I will say, we've got this service, we're calling it CURBy. It's the CU randomness beacon. Before anybody asks, the why is because why not? So CURBy will be launching soon. And as we've gone through and worked with the NIST cryptographers, we've actually realized we're going to be breaking this up into a couple of public services. And here's a sort of Google map of sort of Boulder. And over there is the Gilliland Physics Building. That's where CURBy will be located. And then down at NIST is going to be one of the sources of randomness. And technically, we're going to be creating 2 randomness beacons. One will be this kind of CURBy, which will just be outputting randomness. And we're going to create a second beacon called CURBy-Q, Q for quantum. And that will be salting periodically this other beacon with really good quantum randomness that can be certified and audited. And this is using a loophole-free bell test, which I'll get into later, is the only way that we really know of how to create a source of randomness that can be certified and audited. And in the process of kind of architecting all of this, we realized that we could actually create a third service, which is centered over at NIST, which is a private entropy service. So anybody can sign up and go and actually get certifiable randomness. And we've come up with an interesting protocol for how to do that. I won't go into too many details today, but that will hopefully come online probably in the fall. We need to do some beta testing for that. So this is what I'm excited about launching. I think it's an interesting use case of just a very simple kind of quantum service that has some kind of advantage. And what I want to do is talk to you today about why you'd want to use a quantum random number generator and why I think we have the world's best quantum random number generators. Oh, thank you so much. Okay. I also want to mention really quickly Jasper Palfrey, the programmer who's been working on this. We're not just trying to create these beacons, but also APIs to try and interact. So with this randomness service and make it easier. So just like your phone, you don't usually directly interact with the hardware, you interact with apps. We're trying to do the same thing and create a nice, easy to use API. We've got a number of applications. One of the first demo applications that we're going to be launching is what I'm calling an anti-gerrymandering app. So as you know, gerrymandering is a pretty serious problem. This just to showcase, there's a font called Gerry, which has gerrymandered districts. And you can tell just how ridiculous these are that you can actually create a font. And this introduces a lot of unfairness into our political process. Now, unfortunately, gerrymandering is getting even more subtle, and people are figuring out ways to gerrymander districts along in ways that actually don't look this strange, but give the same kind of results. And so what we're trying to do is the first demo application will be a way that you can actually use quantum randomness tied in with this beacon to draw fair electoral district boundaries. So it'll be a demo application. There's a whole chain that goes into this, but we figured out most of those details. And of course, this isn't a problem that can be fundamentally solved by technology, because gerrymandering is not a technology problem, it's a human problem. But what you can try to do is bake technological solutions into these systems to make it harder to cheat. So I think this is going to be an interesting demo app for this. So when I think about randomness and think about like all the definitions of what it means to be random, to me, randomness, the simplest thing is that it just means something is unpredictable. You can't predict the output and know what's going to happen in advance. So that's my very simple definition, and it's actually going to get us pretty far today. And so there's lots of ways you can generate randomness. You can do cryptographic methods, or you can do physical random number generators. And every random number generator that's in existence, we have three primary issues. So the first one is, okay, I give you a random number generator. Now I want you to tell me how good is that random number generator? Those ones and zeros coming out, like, should I really believe they're random? So there's a series of tests you can run. NIST has their own test suite. There's a number of other test suites that you can run, and you can try to verify how good the random number generator is and if they pass or fail. And it turns out that even random number generators that have a pretty small bias, like I think it's around 10 to the minus, part in 10 to the minus 5 or 10 to the minus 4, will still pass a lot of these tests. So there's not a really good way to even just measure if, how good your randomness is. The second issue is the process that's producing randomness truly random? If I have a cryptographic random number generator that has a seed, somebody else finds out the seed, they can exactly predict everything that's going to come out. Or if I've got a hardware random number generator, somebody might have more information about that. And so I like to use this example of what I consider to be a very good random number generator. You might even call it a quantum random number generator. You take a photon, you hit a beam splitter, and you can send it to one of two ports. And if it clicks here, you get a 1. If it clicks here, you get a 0. And so if you build this device, and I've tried to build some of these devices, what you find is there's, you can take care of some of the biases and other things. There's a lot of work that actually has to go into making this work. But what you're not sure of is, did I miss something? Is there some extra information about the system that's leaking out that could give someone an advantage to either control or predict what's happening? So maybe I think I've got a 50-50 beam splitter here, but really it's a dichroic. And so this photon coming here, maybe its wavelength is changing with power fluctuations based on whatever's driving the source. And if I can control that, and this is a dichroic, I can deterministically control where the photon goes. And so you can verify that you've really got a beam splitter, but now these detectors tend to be temperature sensitive. So you have to really carefully monitor your temperature to really stabilize the system. And what you have to do is you have to construct a model of your device. And you have to understand that model really, really well, because if you don't, there's always going to be somebody who's smarter than you, has more money than you, and is better looking than you, that's going to be able to use that information, those side channels, to predict the outputs. And that is true of any physical random number generator, except the Bell test, which we'll talk about. The third thing is the device physically secure? This, unfortunately, there is no solution to. You just have to have really good safeguards and to make sure that somebody hasn't come in and hacked the computer and just replaced the outputs with a bit string. And that's true of any cryptographic system. You could have the best cryptography in the world, and if you just pay the janitor to sneak into the room and steal the unencrypted text, your security's over. And so we can't solve this problem, but the Bell test will solve these two problems. And that's why I say it's a little bit different, and you have this kind of quantum advantage with entanglement. So people talk a lot about the quantum revolution, and every time they do, I always just have this kind of pop in my head. as what we have to look forward to. And really, when people, I think, talk about like the quantum revolution, really they're talking about three things. And so I decided to sugarcoat this with these Valentine's Day hearts. But really, when we talk about a system, a quantum system, and what gives it its advantage, for me, there's three properties that we really can consider. And the first is that quantum states can't be cloned. And so that's one thing that you can use to your advantage. And to me, that's hand in hand with quantum superposition. It's the fact that you can't clone states. The next is that quantum correlations through entanglement, well, they're stronger than their classical counterparts. And what that means is you can build a quantum computer that sits in a different computational complexity class compared to a classical computer by exploiting those correlations. Or you can build sensors for making measurements that have these like root n improvements, and you can measure things better. And the third property are that these correlations are actually non-local, meaning that they persist over space and time. And so you have these kind of non-local influences where something happening over here can influence an entangled partner somewhere else. And a lot of work has been done to try and show that systems can have a quantum advantage. So one of the first things was to take advantage of this. People proposed things like quantum money that couldn't be cloned. And then that led to quantum key distribution, which is based on no cloning. And obviously people have been trying to show that quantum computers exist and quantum processors exist in a different computational complexity class, and that just a regular computer couldn't simulate them. And these quantum correlations are non-local. Well, that gets into these kind of non-local tests of what are called local hidden variable theories, or these Bell tests, and that's what I work on. And we're going to try to use not just cloning and these stronger correlations, but really also the non-local effects, and use all three of those in the security for our random number generator. So I want to start with a simple example, and I'm going to give the very high-level cartoon picture of quantum teleportation. So because of non-cloning, if you want to take an entangled qubit and move it from one spot to another, you need to do some kind of teleportation operation because you can't make a copy of it and send it someplace else. And so the typical way to do this is, you take a Bell state and you send one partner of the Bell state to a Bell state measurement. And what you'd really like to have happen is for the state to appear on the other side, and you've teleported it to the other end. And unfortunately, when you do this, this doesn't work. What you end up with is something that is scrambled. And depending on what the outcome of this measurement here is you get the state, but it's rotated in some direction. So it's, four things can happen. Either nothing happens, or it's rotated about one axis, the other axis, or the top axis. But that rotation is correlated perfectly with some kind of measurement outcome here. And so depending on that measurement outcome, you just use a classical channel, send that information over, and then you can undo that rotation. And now you've got your state out, and you've destroyed the original copy because you can't make a copy of it. So this is how teleportation works. And it's really using the non-local properties of these entangled particles. But this randomized feature, the fact that you have to use this classical measurement to correct, is baked in because if you didn't need to do that, if you could actually access these local correlations directly, then you would be able to deterministically send information faster than the speed of light. And quantum mechanics forbids that. I believe we live in a universe that does not allow you to communicate faster than the speed of light. And so you're forced, there are these kind of apparent non-local correlations where these two particles share something, but they're an actual random variable. Because if they weren't, then you could access that and use it to deterministically send information faster than the speed of light. And we're going to use that fact, the fact that these non-local correlations have to be random in order to or else you could use them to signal to build our random number generator. And a Bell test is the perfect way to measure and observe these correlations. So I want to talk a little bit about Bell's theorem. And usually this story starts with a historical bent about arguments about the nature of quantum mechanics and, this deep-rooted ease about whether quantum mechanics was truly a statistical theory, or rather there was a better theory that could be made deterministic. And one of the original proposals was that just like statistical mechanics, or if I back up, like classical physics, our classical world, we view it as being in some sense deterministic, in the sense that if you know the position and momentum or all the parameters that go into a system, you know exactly how it's going to evolve. Now, some systems are way too complex for us to measure, like tracking atoms in this room, for example. So you have to rely on statistical mechanics, where you look at average properties. But if we just had good enough measurements and big enough computers, we could deterministically predict how everything's going to behave. And that was the thought, that maybe there's just extra bits of information that we don't have access to in quantum mechanics. And if we had access to those parameters, then we could exactly predict, photon hitting a beam splitter, what direction it's going to go, or any other kind of quantum measurement. And what John Bell showed is that any such theory that has these extra parameters and is local, meaning that those parameters can only affect things in their local vicinity or within their light cone, gives different predictions and results from quantum mechanics. And so that was the historical view of things, is that you want to try and see, is nature governed by these hidden variables, or is it really just truly fundamentally this kind of statistical theory with randomness built in? What people have realized since is that, well, formally speaking, anytime you say hidden variable theory or local hidden variable theory, it's also equivalent to any classical system that's trying to simulate your quantum system. It's equivalent to a hacker who is trying to predict or control your outputs. And all the things that they can do to try and manipulate your system or trick you or use those extra side information to try and figure out what's going on. Formally, all of that is equivalent to a local hidden variable theory. And cryptographically, that's really nice, because it means that with these Bell experiments, which I'll show in a second, you can rule out all of the side channels. You don't need to make that device-dependent model of your system. So you get these what are called device-independent protocols. Now, Bell's theorem, it's, at least to me, when I first heard about it, it was this kind of obscure correlation function that you do the statistical test, and I didn't really understand, why hidden variable theories could only have a certain amount of power, and why quantum mechanics could violate that. But I'm going to run you through this model, and I'm going to do it from the perspective of trying to detect a hidden variable theory. But just remember that hidden variable theories also equal what hackers can do to a system who want to also predict. So we have two parties, Alice and Bob. It's appropriate for Boulder. And Alice and Bob come to us and say, we are psychic, and you can do any test you want, and anything that Alice thinks, Bob will immediately know. Anything Bob thinks, Alice will immediately know. Now, we don't believe in psychics, and we want to come up with a test to show that they're lying, that they're really just trying to share some kind of hidden information. So what I do is I'm going to devise a test, and I'm going to put them in separate rooms. And each room, because I don't want to be in the room, there's a little light that goes off, and when the light flashes, they have to answer. And there's a piece of paper. One side has a plus, one side has a minus. And I'm just going to demand that every time the light flashes, they have to show me either a plus or a minus, and that they always be correlated. All right. So what I'm going to do is I just want to take a quick poll. I want you to show one finger if you think this is a good way to test for psychic behavior. 2 fingers if you think it's a bad way. If you choose 1 finger, be careful which one it is. So if people are ready, you can just hide it from your neighbor if you want to just want to. Okay, oh, there's a 50-50 distribution. Okay, this is not a very good test because they could have shared some kind of strategy for how to answer. So maybe they measure digits of pi, and every time the light flashes, they go to the next digit. And if it's an even digit, it's odd, or it's a plus. If it's an odd digit, it's a minus. They could be looking at, the time. There's lots of things that they could be correlating from their environment. And all of those things could be construed as a hidden variable because they're known to them, but not to us. And so they can actually defeat this test pretty easily by remaining correlated. And so what we're going to do is, and in fact, the simplest strategy is they just always show plus. Then they're always correlated, they win. So we're going to do a more clever experiment. And this experiment is going to now add a second piece of paper. So now they've each got 2 pieces of paper. Same thing, each paper, they can show a plus or a minus. And I'm just going to label them A and A prime, B and B prime. And I've got the lights in front. And so I can choose as an experimenter whether Alice has A prime and Bob has B or B prime. I can choose which paper they answer from. And we're going to do the exact same rules as before, where we're going to demand that they be correlated in all possible cases. And we're going to give them a point if they get things right. We're going to take a point away if they're wrong. And so in particular, the game that we're going to play, it's a little bit different. But if basically the outer lights go off, so if it's an A-B setting, then we demand they be correlated and show the same answer. If it's an outer and inner light, they also need to be correlated. So those are 3 cases they need to be correlated. But if it's the inner light, they now need to be anti-correlated. So now there's an extra piece of information here where Alice, when her inner light goes off, she doesn't know if Bob's inner light went off or his outer light went off, and doesn't know how to answer, doesn't know if she should be correlated or anti-correlated. And the same thing happens for Bob. And so we can play this game. And so if they're psychic, they just win every time. They're going to get a perfect score. But we can kind of look at the expectation values on average. And it turns out like you can come up with incredibly complex strategies, but an optimal strategy is for Alice and Bob every single time just to answer plus. That is also an optimal strategy in this case too. And so when you do that, then 3 of the times they're right, 1 of the times they're wrong, and they lose a point. So they get an average score of 2. And John Bell rigorously showed that any kind of hidden correlated strategy, right, that's the best you can do with it. But if Alice and Bob instead used a quantum resource to make their decision, so now they've got an entangled set of particles, and you send 1 to Alice and 1 to Bob, then what you can do is they can make measurements on their entangled states and let those, whether or not a detector clicks or not, that's whether they report a plus or a minus. And you can use this type of scheme, and you can actually do better. You can actually win more often and get a score of 2√2, which is bigger than 2. And that's what a Bell test does. It shows that quantum mechanics and through entanglement in these Bell states, you can actually do better than you can with classical mechanics. And these kind of local hidden variable theories, they're also, all the things that you've used to try to, on your classical computer, to try and simulate what a quantum computer does. You're really ruling out a very broad class of really like how nature behaves. And so in our particular case, what we're going to be worried about, in 2015, we did this experiment where we closed all the loopholes and did this, I think, conclusive experiment ruling out local hidden variables in nature. But you can take this now and say, instead of trying to rule out this hidden variables in nature, can we rule out anything a hacker could do to try and influence the correlations that we observe. So oftentimes when I give this talk, I preface this with the teleportation example to show that you can't actually use this entanglement to send information faster than the speed of light. But this is something that almost everybody asks, or somebody will ask. So no, you can't use this to violate locality. You can't signal with it. All right, so just to kind of tie up this story, with this experiment, now there's a number of loopholes or ways that Alice and Bob could still cheat. So the first one is if Alice and Bob are really close to one another, they could just text each other, hey, I got this light flash. What did you get? And then they could correlate their answers. So what you could do is move Alice and Bob far apart, put one on the moon and one on Mars. And then you could demand that they answer fast enough that there's no way possible for them to send information at the speed of light to one another. That's outside of the NIST budget. So we're going to use photons and go, maybe like 100 meters or so instead. The second way that they can cheat is if there's something with these random number generators that is, dictating what the measurements are. So if Alice can figure out what Bob's measurement is in advance, just by knowing something about the random sequence, then that can spoil things. So you need to have really good random number generators that are independent of one another. And then the third thing is Alice and Bob, every time Alice gets that A prime setting, she can just refuse to answer and just say, sorry, technical malfunction. And so, something went wrong. I didn't get it. So we're going to have to force them to answer a certain fraction of the time. It turns out you need to answer at least 2/3 of the time to close any kind of loop that's kind of what's called the detection loophole. And so loss is going to be very, very important. We really need to do this experiment with very, very low loss. So this is just to restate that those loopholes are called the locality loophole, freedom of choice, and making no kind of fair sampling assumptions or detection loopholes. So since we did our experiment, there's actually been a number of experiments that have loophole-free setups. The first one at Delft, they used nitrogen vacancies in diamonds to do their experiment. It's separated by, I think, 1.3 kilometers. A very impressive experiment. We did our experiment in 2015 over at NIST, and I'll talk about that. Vienna, we also collaborated with the folks there with Anton Zeilinger's group to help out with the detection, and I traveled to Vienna to help set up some aspects of that experiment. The Hofburg Palace is shown not just because it's symbolic of Vienna, but because that's actually where they did the experiment. They wanted a long hallway, and so it turns out that there's these it's almost like dungeons down in the palace, these long kind of corridors, and where I think where the nobles would escape out of or something if something happened. And some of them haven't been used for decades. And it turns out it's a very historic place to do an experiment, and it's a terrible place to do an optics experiment because there's just lots of dust. The tram lines were running above it, which kept messing up the detection system. But the experiment worked, and there was a lot of interesting kind of historical challenges that came out of that. We also have Harold Weinfer's group in Munich that has done some nice atom experiments, and also in Hefei, Jean-Louis Pan and Chang Zhao, their optics group, now have multiple belt experiments up and running. So in 2015, we built this test, and this was the original version of the experiment. And this is a picture of NIST as it used to be. Since then, this wing has been demolished at NIST and then rebuilt, and that's actually where we're now housed. And I'll show you a new picture of that. But the original setup, we created an entangled pair of photons here, sent one down this long hallway, 131 meters, to an Alice station, and then another photon down to Bob, 126 meters away. And so Alice and Bob were located about almost 185 meters apart. And this is not an optimal setup. You really want things to be in a line to get the best space-time separation. It's the most efficient, but we could make the diagrams work. It was quite complicated. And a big part of the problem was that, you can't just go and kick people out of like offices and lab spaces. These were the spaces that were available that kind of worked, and we could make it happen. And the first experiments were done in 2015, and the first loophole-free test. We also were part of what's called in 2018 the Big Bell Test collaboration, where a bunch of groups around the world, I think it's a great science outreach experiment, where a collaborator of mine, Morgan Mitchell, they wanted to see if, instead of having random number generators pick the basis choices, what if you had humans make those choices? And of course, we can't put people in the lab and do things quick enough. So they did the closest thing possible, which is they had people from all around the world, like I think something like over 100,000 school children around the world, basically played this random game where they clicked ones and zeros and submitted those. And we used those inputs to verify the Bell test. We didn't see anything different, as one might expect. That was the most interesting thing that came out of this, is that humans are actually quite, we know that they're not, human inputs aren't very random, but we figured if you take 100,000 people all playing a game to submit zeros and ones, that an equal number would just be off by zeros as you would have off by ones. But there was about a 5% bias towards zeros, which was quite surprising to us, and we didn't anticipate, and made the analysis quite difficult. And it turns out that most humans, the majority, are right-handed, and you tend to hit the zeros with your right hand, and we didn't account for that, and that's why you need social scientists at any time you're going to deal with humans. So we've also done we've done a number of randomness generation experiments. We did the first kind of what's called device-independent randomness generation in 2018, and we've had some improved results where we've made things much, much better in 2020. And we've also done this setup called a randomness expansion, which is a very, very hard version of this. And Mohammed here is the one back there who did a lot of the theory for that work. So this is the current version of the loophole-free Bell test that we started setting up just as COVID hit. And unfortunately, there's a lot of fibers that need to be run. COVID really has slowed things down. But right now, we're going to be in this newly built Wing 3. We've got a lab, because we're not trying to violate local realism, just a hacker, we can use this different configuration where the source and Bob stations are actually pretty close. And Alice is down here. And so I'm going to show you just a little animation, or pseudo animation, for kind of how things work. But at time t equals 0, we use a nonlinear process here at the source to produce a pair of entangled photons. And this is a down conversion crystal. It's a Chi2 process. And it allows us to sometimes produce a pair of photons. So you take a photon and you fission it probabilistically into a pair of entangled photons. And there's a lot of work that goes into designing that I'm just going to gloss over. But I'll say it's maybe the best entangled photon source in the world. We have one of the metrics that people often use are an entanglement visibility. It's a measure of the entanglement, and it's or at least an estimator of it. And we've measured our entangled states in like 360 different bases and observed the correlations, and they're very, very high. So this is extremely good. Most people report 2 bases. We did 360. So at t equals 0, you produce the pair of photons, and now one gets sent to Bob, and it's coupled into a fiber and just stored in a loop of fiber. And then the other travels down this hallway, and then it keeps traveling. And when it reaches this point, then at Alice and Bob, we've got this measurement set up, and we fire a random number generator, and that starts the process of we're going to be using polarization to encode our entangled photons. And so we start the process of firing this Pockle cell and picking the random number, and we do that simultaneously at both the Alice and Bob stations. So what happens is we have to fire this Pockle cell early enough that the or the random number generator early enough that the photon, by the time it reaches the station, it will be ready to be measured. And so we fire this up. Really, we're going to be using at Alice and Bob 2 different measurement angles. And so these are some wave plates, and this is the Pockle cell that allows us to do the fast measurements. It operates about 200 kilohertz. And then we go to these detectors, and this really is one of the enabling technologies, is the detector work that Sewunam, Varun Verma, and Dilip Reddy have done. They've actually managed to make our single photon detectors now, the latest batch, up to 98% efficient. So there's almost no loss, and that includes like any fiber splices and stuff. So they're just about perfect, and we're very excited about this. So once that photon arrives and starts to be measured, the random number generator. So once the photon arrives to be measured, information about that random setting starts to expand in this kind of light sphere. And we have to complete the measurement at Bob before any information about Alice's setting arrives, and vice versa. And we complete the measurements with about 32 meters to spare in this diagram. So we could have actually made the stations closer, but again, these are the rooms that we have available, and it doesn't really hurt us in terms of loss going those extra few meters in fiber. So we can basically make measurements that are non-local. So Alice and Bob's measurements cannot influence one another in any way. So how do we compute a Bell violation? There's the typical way is to measure something called a CHSH inequality. There's but there's more sophisticated statistical methods now that have been developed. And in particular, this is like what Mohammed and Manny Neal and Scott Glancy and a few other theory collaborators over at NIST have developed as a whole framework for generalizing how to interpret Bell inequalities more statistically. And for our particular experiment, the most frequent thing that happens is nothing. We don't produce a pair of photons. It turns out that those don't actually hurt us. Those don't count in the Bell violation. It's only when we actually do prepare a pair of photons that things matter. And we've got very low loss in the system, only about 17% currently in our current setup. So there's 16 things that can happen. So there's 4 different measurement combinations. And for each one, you can either both parties don't detect a photon, one party detects a photon, or they both detect a photon. And this is the experimental distribution. This is what we get. This is the closest hidden variable theory, or somebody who was trying to fool us into thinking that we had some kind of entangled results. This distribution is the closest a hacker or anyone else could come to trying to simulate this distribution. And they look very, very close to one another. And they are. But if you take the difference between those two, it turns out that there's enough counts and enough differences between them that you can statistically rule out and measure the distance between those distributions effectively. But I'm glossing over a lot of things. And this difference between them, that is the amount of, that's a measure of the true entropy or the true randomness that was in the system. That, the best you could do to try and predict our results was this bottom red distribution. And the fact that you can't do that exactly, that's this green, that's a measure of that entropy. And so we can take that entropy and that measure, and the Bell test tells us how much we have and how good that is. And we can take that now, and here, this is a picture of the outcomes in our experiment. And the red dots are in blue are when only one party detects a photon, black is with one. There is, I promise, stuff on this slide. And so if we zoom in just, in some small region, it's very, very sparse. Like, again, most of the time we have just zeros. But that Bell test, the difference is that within this sparse data set, we know we have a certain amount of randomness, and that's true, and that we can certify. So we need to go through what's called an extraction process. And to me, it's very much like how you take, create olive oil. You take olives and you press them down and you get the good stuff out that you really want. And there's a lot of theory that goes into all of this. And so it turns out that if you have a bit string and you know how much entropy is in it, and you can give a bound on how much you have, which is what the Bell test gives you, then there are methods, cryptographically secure methods against even a quantum adversary that can allow you to take that raw data, the information about how much entropy is in the seed, and you press it and extract it, and you can get, these good random bits out. So what does this mean that it's certified to be uniform within a part to 10 to the minus 20? Well, what you'd like to know is just how uniform or even that distributions of ones and zeros is. And the most basic measure you can do is to just measure bias. How many zeros do you have? How many ones do you have? And if you wanted to, measure a bias, which is the simplest metric here, of a part in 10 to the minus 20, you actually need to have 10 to the 40 bits. It's a square root of everything. So you want to measure a deviation from a part in 10 to the 40, then that's like 10 to the 20, then you need 10 to the 40 bits. 10 to the 40 bits is a horrific amount of data. How horrific? Well, the world's best random number generator right now in terms of speed, not quality, but speed. There's this paper published very recently in 2021, about a year ago, in Science, where they use lasers on a chip to create what they estimate would be something like 250 terabits of data per second, of random bits per second. So if you ran this thing for, I think it's something like 1 billion lifetimes of the universe, you would get to 10 to the 40 bits. So it's a huge number of bits that you would have to acquire, and it's just not possible to verify any kind of random number generator, the quality, to the level that we can with the Bell test. And the Bell test, we can do that because we can rule out any kind of, we have a measure of just the amount of true entropy in there. So there's a really interesting true quantum advantage to this. You can do a task that you can't do any other way, even with the quantum system. And this is guaranteed secure, not just against a classical hacker, but a quantum hacker too, because of the no cloning theorem. You can't just take a quantum computer and somehow entangle that and predict the outputs. All the security proofs are robust against that type of attack as well. And okay, so 512 bits also might not seem a lot, but right now there's a cloud computing company called Cloudflare. They do a lot of online security. They use randomness. That's a integral part of their security. And their state-of-the-art random number generator is a webcam looking at fluid dynamics on lava lamps. So, we're not trying to go against every random number generator, but there are niche use cases where you'd want something that could be certified much better than maybe something like this in these type of rates. So this is kind of our competition. So our goal, the first version of the experiment, we could do about 512 bits certified to that level in about 5 minutes. This new version that we're about to get running, and in fact, I think this week we're going to be getting our first data coming out. We're optimizing. We're hoping to do this in less than 10 seconds, and this is what's going to be fed into the beacon. And we've also got some collaborations, and we've got a few more things on this table. We've now got a 20-foot long table. We're actually setting up a third generation where everything's going to be loophole-free on a 20-foot optical table. And so the two ends will be space-like separated, and that's going to give us another couple orders of magnitude and speed increase. A big part of this is just making those measurements fast enough. So now we can go to gigahertz measurements. If you want to manipulate the polarization of a photon at 50 gigahertz, you can buy a commercial component to do that if you're willing to put up with like 60% loss. We can't, so we have to basically make our own, and we've had to figure out how to make low loss few percent modulators that can operate at like the gigahertz level. We also have plans to try and shrink this down even further. The Gen 4, we've figured out a new encoding scheme that's going to make it about the size of a pizza box and not even a large pizza box. And then from there, that encoding scheme will go onto a chip. And eventually, we'd like to have this be something where you can just have a nice little box that you can sell people, and they can have their own certified source of randomness. So my last little plug is it really necessary to close all of the loopholes? And there's a lot of people who are quantum information theorists that say that no, it isn't. We don't care about local realism. We've already ruled out nature. And, so why do you care about making things go far apart? Well, it's because, again, of those side channels. You want to worry about anything that could correlate your results. And we planned on building a hacking demonstration to show that you could actually hack the system if you weren't far enough apart or you relax some of these constraints. And then we hacked ourselves accidentally. So one of our colleagues, he gave one of the CUbit seminars, I think last year or a couple of years ago, Franco Wong, has been bugging me for years. He said, you're efficient enough, why don't you just go do the original simple CHSH Bell inequality where you need more than 83% efficiency, which we didn't have for a long time, but now we do. Why don't you just do that measurement? And so we did this on the tabletop just before the pandemic ended. We didn't do the fast modulators. We just had, because we didn't want to be space-like separated, we just used wave plates, but we could close the detection loophole. And so because of that, you can try to see how close can you get to the quantum bound of 2√2. And that's sort of been like a mark that a lot of quantum photonics people try to do, is like, I'm even closer to that bound. So 2√2, it's like 2.828 something. So I did the first measurement and I got a value of 2.83, which is bigger than the quantum bound. But it was like a 2 sigma violation. So I laughed and, okay, whatever, we'll do this again. And I just kept violating it. And then finally I got like a 14 sigma violation, which should be significant and quite exciting. But what we realized is there's this really weird, very subtle effect, because we're using detectors that are in the same fridge, where there's a correlation between these two, and this kind of bizarre crosstalk that we've had to isolate, which we wouldn't have seen if we were far enough apart. So it's a guard not just against someone else coming in and introducing on weird side channels that you haven't considered, but it's just a guard against yourself as an experimentalist. Like, you don't have to be clever about trying to lock down every possible thing. So I like this because it's a way to take, we do need randomness to kind of seed this process to make these decisions, but it's a way to take good random number generators and turn them into these like fantastic certifiable sources of randomness. So just to wrap up, what's next? Well, in the next few months, we're going to be hopefully launching CURBy and CURByQ, and then maybe some other interesting cryptographic services that kind of dovetail in with that. And it'll be a way for us to make available this system that has, I believe, a true quantum advantage. You can do something different available to the public. It's maybe not, we're not building a quantum computer or anything as audacious as that, but we are making kind of quantum 2.0 service available to the public. And we really want to also shrink this down so it's a much more stable system, much more compatible, cheaper to run, and you can actually turn it into a product. And there's also interesting ideas that I haven't talked about today, not necessarily using polarization encoding, but there's actually ways we can generalize this to quantum networks to make really interesting non-post-selected all optical quantum networks. And so we've got some interesting ideas there. And so I'm very excited about that and some of the extensions and generalizations to these new kind of quantum computing, or not quantum computing, but quantum communication ideas. So with that, I'd like to say thank you and take any questions. Very carefully. We looked at a number of different options, and this has actually got a grant with Paul Kwiat in Illinois to look at this. And so we wanted to try and build something fast, and so we looked at using a nonlinear optics approach. So could you use some kind of nonlinear phase shift, like a Kerr effect with an intense pulsed laser that would co-propagate? Like Prem Kumar had some initial ideas, and I think people have been looking at trying to do these, more fancy switches in using there's a couple of different ways you can construct kind of a nonlinear phase shift to really use an intense pulse of light to modulate your single photons. And when you start looking, it's just hard, and there's lots of noise and lots of loss that comes in inadvertently. It's hard to actually get that to the kind of performance requirements we wanted. And then Paul was just said, you know, how does a pockle cell work? Well, you've got a material and it's got some electro-optic effect and you have plates on either side. And the amount of voltage you have to apply determines the phase shift you see or the rotation of the light. And it's just a capacitor. And you need typically kilovolts to run these things, which means the drivers are hard to run. And so you can't run them very fast. And so he said, why don't we just make them smaller and thinner and sort of kind of go between where you'd be with the waveguide and that intermediate regime. And so we've looked at it and we figured out how to make very thin, like 500 micron thick pockle cells, basically. And they seem to be working. We got about 2% loss through them. The initial testing was done where we're doing it right now, but I think we could do them very, very low loss. And you can now buy, this has coincided with a lot of these like MOSFET electronics that you can now sort of drive up to like say 60 volts. So this combination of being able to now run these things at gigahertz rates because of the lower voltage requirements, it's just making things smaller.
I'm curious about things like the gene code having applications in this.
Yeah, so just to repeat the question, can chain Bell inequalities be used to, like for these device independent protocols, or do you get any improvement? And what a chain Bell inequality is, you actually can make more measurements that are linked, and you can basically rule out more of a, like the hidden variable theories. You can say, okay, well, the correlations, maybe I got a value of like 2.4 for my Bell inequality. That's bigger than 2, but the local hidden variable theories can get up to a value of 2. The chain Bell inequalities drive the local hidden variable content down to basically 0. And so in principle, you would think that you could do better with the randomness extraction, but it also turns out that you can't use as many of the correlations. And so, you know, I've asked other people about this, like Manny Neal and whatnot, and it's not clear. It hasn't been worked out, but I think the intuition is it's kind of a wash. Like you gain, but you in some areas, but you lose in another, and they kind of cancel. So. It's free, so yeah. These beacons are very low cost to operate. Oh, I mean, okay, yeah, the NIST side of things is expensive because you need PhD students and lasers and everything else, but that's funded. So yeah.